So what we're going to do here is I'm going to change my share to this. We're going to look at number one, determine the Lewis structure of dinitrogen monoxide, and then check your answer. Did your Lewis structure match the one found with the internet search? So here we go. I'm going to do another change share here. Use share. Okay. Let's see. This doesn't look like it's zoomed properly. That's a little better. And we're going to get the Lewis structure of dinitrogen monoxide. So the first step is to count valence electrons. Each nitrogen has 5, but there's 2 of them. Each oxygen has 6 and there's 1, so I'm not going to bother multiplying by 1. And we get 16 electrons. Fair enough?
Right.
Now, I'm going to show you the mistake that most people make.
Mm-hmm.
This is what you start with. And that's your first mistake.
Yeah.
The reason
I did it right.
This is a mistake is because when you choose your central atom, you choose the one that tends to make more bonds. Nitrogen tends to make 3 or 4. Oxygen tends to make 2, 1, or 3. So what we do is we compare the usual to decide which one's going to be the central atom. Nitrogen can make more bonds than oxygen normally, so nitrogen's in the middle.
Right.
So I'm just showing you the first mistake that people make.
Mm-hmm.
Secondly, you put electrons as lone pairs on the terminal atoms,
Mm-hmm.
and you put it on the more electronegative atom first.
Oh, okay.
And for electronegativity, this is the way it works. This is higher electronegativity. So that means any atoms in a period, the one to the right is more electronegative. So if we look at carbon, nitrogen, oxygen, fluorine, fluorine is more than oxygen, oxygen more than nitrogen, nitrogen more than carbon. And this is the way it works in a group. So fluorine is more than chlorine, chlorine is more than bromine, bromine is more than iodine. So it kind of all funnels to the upper corner where fluorine is the most electronegative atom, okay?
Okay.
These second modes, you should know number 1 and number 2. Number 1 is fluorine. Number 2 is oxygen.
Oh, sorry. Let me close the door.
Sure.
Okay.
Okay, so we're going to put the lone pairs on oxygen. We put as many as we need as 2 dots called lone pairs until we get to 8. And when I say 8, until we get to 8 electrons total, understanding that a bond represents 2 electrons. So we have 2, 4, 6, 8 around oxygen, and we're done with that oxygen. Then we move to this nitrogen. We're going to do the same thing, 2, 4, 6, 8. And now, if we have any remaining electrons, we're going to put all of them on this nitrogen in the middle. But we don't have any, so we can't put any there. So we're kind of stuck. Now we look and see, do we have an octet everywhere? And we don't. And we want an octet on this nitrogen. So there are 3 ways of doing it. One is this way. I'm going to draw it, and then I'm going to tell you how I got there. So first of all, do you see that on this nitrogen on the far left, there used to be 3 lone pairs, and now there's 1. Well, one of these lone pairs I turned into a bond between the 2 nitrogens, and the other lone pair I turned into a bond between the 2 nitrogens, and the third lone pair I left alone.
Okay.
So the question here is, why did I turn 2 lone pairs into bonds? And the answer is, so I could end up getting an octet on nitrogen in the middle. And now this oxygen, now this nitrogen has 8 electrons, 2, 4, 6, 8.
Right. So I got something similar to that, but not that. So I guess that's where,
Well, I've got
um,
2 more to show you.
yeah.
Another one we could do is this one. So how did I get to this one?
Yeah, so you just took the lone pairs from the oxygen.
Right. And the third one is this one. How did I get to that one?
You just took one from each side.
Right. And in each case, the nitrogen has 4 bonds, the nitrogen in the middle. In each case, the nitrogen in the middle also has 8 electrons. That was our real goal.
Hmm.
In each case, the nitrogens on the end have 8 electrons by a combination of lone pairs and bonds. And in each case, each oxygen has 8 electrons, or an octet, by a combination of either bonding electrons or lone pairs. So the thing that we need to do is decide, is one of these better than the other? And we do that by assigning formal charge. Now, to assign formal charge, there is a formula for it, but basically a formal charge is the charge an atom has in a compound compared to its valence electron dot symbol. So here's a better explanation. Nitrogen in group 5A, whoops, here's nitrogen, has 5 valence dots. Those are valence electrons. So a neutral nitrogen atom has 5 valence electrons. In 6A, oxygen has 6 valence electrons. So nitrogen has 5, oxygen has 6. So if you see an oxygen atom with 6 electrons, you say, oh, its formal charge is 0. But if you see an oxygen with 7 electrons, you say, oh, its formal charge is -1, because in order to have 7 electrons, a neutral oxygen would have to gain an electron and gain a negative charge. Okay?
Hmm.
So formal charge is the charge it should be if it were neutral compared to what you see in the structure. So in
Right.
the structure, how many of these electrons belong to nitrogen? Do all 8 of them? And the answer is no. This nitrogen, the 2 that are not bonding to anything else, belong to that nitrogen.
Hmm.
These are 6 electrons total. And the formal rule is half go to one atom and half go to the other. So since there are 6, 3 of them go to this nitrogen and 3 go to the other nitrogen. So if we look at this, nitrogen normally has 5 dots and this has 5 dots. What does that mean about the formal charge? It's 0 because it has exactly how many dots it should have.
Right.
This nitrogen has 3 dots from these 3 bonds and 1 dot from that bond. So what happens to a nitrogen with no charge on it when you take away an electron? It becomes +1.
Hmm.
And this oxygen is going to be a -1, following the same sort of logic.
Hmm.
Now, this one I actually did a different way. I didn't count dots. I said, well, if that's a 0 and that's a +1, I know that whatever number that is, these 3 numbers have to add up to 0 because that's the charge on this thing.
Hmm.
Okay, so what's the formal charge on this nitrogen that I'm pointing at?
It is 1, 2, 3, 4, 5, 6, 7, and it's supposed to be 5. So it's 2 extra electrons.
That's right. So what does that do to the charge?
-2.
Absolutely. What is the formal charge on this nitrogen in the middle?
+1.
Yep. And you don't really need to do this one again because we already did it. A nitrogen with 4 bonds, +1. How about this oxygen? We haven't seen one of those, an oxygen with 3 bonds.
I thought it was +1.
Why do you think it's +1?
Um, because we have 5 electrons, but it should be 6.
Should be 6, so it's devoid. It's missing an
It's
electron.
missing an electron, yeah, so it's like positive.
And look at what these numbers add up to. What do they add up to?
Right.
Which is what they should add up to.
Should add to
There's 2 ways
0.
to get it, right? So 2 ways to get that last oxygen. How about this nitrogen?
That is 1, 2, 3, 6. So it has an extra electron, so it's -1.
Correct. How about the middle nitrogen?
The middle nitrogen is missing an electron, so it's +1.
Right. And how about the oxygen?
The oxygen is, oh, sorry, let me write this down. And the oxygen is, what is it, 6 electrons? So it's good.
Right. So it's
0.
0. Okay, so here's how we analyze these different structures. By the way, these are called resonance structures. Here's how we judge them. If you see a -2 on your resonance structure, or a +2, or -3, or a +3, or anything that's not a 1 or a 0, we eliminate it. So
Okay.
this is no good. Now, for the others that remain, here's how we judge them. If they are all 0s, that's the one we want. And you get rid of the rest.
Okay.
So all 0s, that's the hero. You with me?
Right.
0s are the best. Now, here, they're not all 0s. They're either 1s or 0s. But at least they're not 2s. Now, if you're going to have a negative formal charge on a molecule, you want it to be on the most electronegative atom, not the least. So what's more electronegative based on my little chart here, oxygen or nitrogen?
Oxygen?
That's right. To the right is more electronegative. So we want that -1 to be on oxygen, which it is here. And how about over here?
It's not. It's a
Not.
0.
So here we'd say this one is better.
That's the best.
This one is not better. And so this is the best.
Best and then
So the
not
best
as
and the
best.
worst. And this one, it doesn't even count.
So that's something that I was kind of fuzzy about after yesterday about the resonance structures, because I guess in my head I thought resonance structures, they all had to have 0s, because you showed that example of where you had 3 versions of it and they all had to be included, because you know what I mean?
Well, I think in the example I did yesterday, they weren't all 0s, but the combination was such that the -1 was always like on oxygen or something like that. And that's fine. But the positives and negatives floated around. Do you remember what number that was?
I don't.
I don't either. But at any rate, if usually when you get to a structure and you get all 0s, there's only one resonance structure that's going to have all 0s. So you say, that's it, the rest don't count.
Right. So because we had an example where we had to include all 3 of them, right? So in this situation, this example, we have to choose the best one.
Yeah, and this is the best one.
So that's the one we would pick and disregard the rest.
Well, actually, in this one, you can't disregard this one altogether. You got to say, well, it looks like this and this, kind of a combination of the two. Now, as far as it being a combination of the two, which one does it look more like? The real structure, what does it look more like?
Probably like the
better one.
Yeah.
That's it. It's just like when, I don't know, people have kids, right? And sometimes the kid looks like a perfect mix of both parents, right? And sometimes the kid looks like the splitting image of the mother. And sometimes the kid looks like the splitting image of the father. And you're like, oh, you look so much like your mother. And it's true. So it's kind of the case here. Like maybe this one looks more like the mother and this one looks more like the father.
But we had a situation yesterday where they were all the same. They were all equally
Right. And it may have been a case like this. Where here the formal charges are -1, -1, 0, and 0. Now, whenever you have an ion, you're supposed to put a bracket around it and the charge on the outside. Now, a resonance structure with this is this one. -1, -1, 0, 0. And the last resonance structure looks like this. I'm going to try and get my hand out of the way as quick as I can. And this is -1, 0, 0, and -1. So all three have to be included. Why do all three have to be included? Well, let's analyze this. Which one of these has all zeros?
none.
None of them. Okay, shoot. Which one has the most number of zeros?
They all have 2.
Okay, so we can't use the most number of zeros. This one has a -1 on an oxygen and a -1 on an oxygen, right?
Mm-hmm.
Where are these -1s?
They're also on oxygens.
Okay, so that we can't use that as a tiebreaker. Where are these -1s?
They're also on oxygens.
Okay, so we're done. I mean, there is no way to say one is better than the other. So that means they're equal. There is no best one, they're equal. Okay?
Yeah. Yeah, this helps a lot. My last question was really for the last part of number 1.
Okay, let me change to looking at that question here. Okay,
Yeah.
so let's actually go through these very quickly. Did your
Okay.
Lewis structure match the one found with the internet search? And if not, why? Well, you could say based on the internet, sometimes the internet says this one, and that's it.
Mm-hmm.
And when I say this one, you can't see it because I'm not showing it to you. The internet may say, you know, depending on where you go for your information, you could get all sorts of answers, but you might get all three of these. And then you might get one site that says, oh, this one and this one, but this one's better. And then you might get another site that says, oh, this one, just because it's better. So you have to be concerned with what site you go to. And when I say you go to one site versus another site, they could both be .edu sites. And what you're getting is one professor's opinion. Okay? Now, if we go to the next question here, so I'm going to change my. So draw all of the resonance structures that provide an octet for each atom. So that's what I've done right here for draw all of them. So do you see that they all have octets?
Yeah. Mm-hmm.
And then we just did the formal charges and we evaluated them. Better,
Mm-hmm.
no way, worst. Okay?
Mm-hmm.
Which structure has essentially no probability due to formal charges greater than 1? And that quote 1 means greater than 1 or -1. This one.
Right.
Based on the remaining structures, which is the best? The one on the left.
Mm-hmm.
Assuming these are equivalent, so that this is not best and this is not worst, but they're equal.
Mm-hmm.
What are the bond orders in N 2O. So if we look at this, the bond order between the nitrogens is a 3, and the bond order here between the nitrogen and an oxygen is a 1. So how do we get bond order? I'm going to show you here. I'm going to try and look at what I'm writing. That's good. So here, if it's a triple bond, the bond order is 3. If it's a single bond, the bond order is 1. That's how you assign bond order. So here, what are the bond orders between the two nitrogens?
2 and 2.
2 and 2. Now, when the structures are equal, the actual bond order is averaged. So here I'm just putting NN and O so that we know it's between nitrogen and nitrogen and oxygen respectively. So if they're equal, we get the average bond orders. So what's the nitrogen-nitrogen average bond order if we have a 3 and a 2?
5 divided by 2.
2.5.
Mhm.
What is the bond order for the nitrogen-oxygen?
What is it? 1 and 2. 3 divided by 2, 1.5.
1.5. Okay, so that's the average. Fair enough? Now, let's take a look at the question, the next part, because this is the more interesting stuff.
Yeah, that's where I started getting really confused.
Okay, given the following bond lengths and the actual bond lengths in N2O, which resonance structure, it should say singular structure, has the greater contribution to the overall structure of the molecule? Briefly justify. So what I'm going to have to do here is draw the two major ones again. And here's the other one. Okay, so those are our two resonance structures that we have, right?
Yeah.
Okay, now in the real molecule, when we look at the N, and the O, in the real molecule, it says the actual bond lengths are, I have to move something to see, 112 picometers and 119 picometers. So that's actual. Are you with me there?
Yeah.
Now, take a look at the resonance structures. What is a typical nitrogen-nitrogen triple bond length?
Mm, 2.5 or?
Oh no, bond length. So let me see what I'm sharing with you. Here you go. Here's the list. What is your
yeah.
nitrogen-nitrogen bond length for a triple bond?
Triple one, it's 110.
110 picometers. And what is it for a nitrogen-nitrogen double bond?
Oh, sorry, you kind of slowed down there a bit. Sorry, like I couldn't hear what you said.
What is I probably pointed my mouth down. What is a bond length for a typical nitrogen-nitrogen double bond?
120.
120. So let's look at this number down here that is actually the bond length and compare it to these two numbers. What is this closer to?
So the 112 would be closer to the triple.
Yeah. No. Come on. 112 is closer to 110 than it is to 120, right?
Right.
I mean, all you have to do is get rid of the one in front of here and say 10-year-old, 12-year-old, and 20-year-old.
Yeah.
This 112 is closer to the 10-year-old, right?
Right.
Okay. Way closer. It's only 2 away. Now, the typical nitrogen-oxygen bond length for a single bond is 147 picometers. And for a nitrogen-oxygen double bond, it's 115 picometers. So if we take a look at these numbers here, I'm going to move this down. This is what a single bond is, so 147. This is what a double bond is, it's 115. Look at what it actually is. What is it?
119.
So what is it closer to? Is it closer to being like a double bond or a single bond?
The double?
Closer to a nitrogen-oxygen double bond. Okay, so which of these two resonance structures did we say is probably more important? This one's more important, right?
Right. Mm-hmm.
Okay, and that bears out when we look at the nitrogen-nitrogen bond length, but when we look at the nitrogen-oxygen bond length, it actually goes the other way. So that's kind of interesting, isn't it?
Mm-hmm.
Now, I didn't ask you this, but can you think of a reason why that may be?
Because it's an average? Or
Here's what I would say. The reason we may like this one better is because that nitrogen has how many bonds?
3 bonds?
3. How many does it normally make?
The nitrogen normally makes, it has multiple ones.
Well, here's
Normally makes 3, but it can make more.
It can make more, but it normally makes 3, right?
Right.
So why do we say normally makes 3?
It's the most common.
Most common. Why is that the most common? And the answer is because it's the most stable. Okay, how many bonds does this nitrogen make?
2.
Okay, so it seems like the more common bond length is going to be, the real bond length is going to be closer to the more common bond length. You with me?
Mm-hmm.
Okay, look at these 2 oxygens. How many bonds does oxygen usually make?
2.
So this is more common, right?
Right.
And maybe what we're really seeing here is that the bond length is closest to the more common number of bonds that atom makes.
Oh, okay.
Now, why am I ignoring the nitrogen in the middle and saying, hey, wait, that's got 4 bonds? And the answer is because here you've got 4 bonds, here you've got 4 bonds, so it doesn't really matter.
Okay.
Okay.
Mm-hmm.
So when we go to the question here, and I'm changing my screen, assuming blah, 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 which resonance structure has a greater contribution to the overall structure of the molecule? I'm going to say, well, that's kind of a red flag. It looks like they both contribute because in this case, this bond length, this bond length is closer. And in this one, this bond length is closer, right?
Mm-hmm.
So I'm going to have to say, you know what? They both look like they contribute pretty equally.
Okay.
You with me? So it's
Yeah.
almost like